Hello, Chem 1A. This is Chapter 11, Lecture Video 1, and we're going to be covering really molecular orbitals and hybridization in this chapter. Now, what that really means is we're going to be talking about not just why things bond, but really what's going on when we form a covalent bond. And there are two major approaches to how this is done. One is known as valence bond theory, and the other is known as molecular orbital theory. In addition to those two topics, at the beginning of this lecture and this chapter, we're going to be talking about molecular shapes, what shapes our molecules take on, and how to determine them.
Molecules have different shapes depending on what's around the central atom. Now, molecular shapes are predicted by what we call VSEPR for valence shell electron pair repulsion theory, or VSEPR for VSEPR for short, as an acronym. Now, VSEPR predicts two different types of geometries: molecular geometry and what we call electron pair geometry, or what I like to call, instead of pair here, electron group geometry. There's a reason for why I don't like that word pair. Some textbooks still use the word pair. Some textbooks are starting to change over to this word group, which I think is a much better descriptor as far as the name. So we'll talk about each of these in depth throughout the next couple slides. So molecular geometries really describe the molecule in terms of the atoms surrounding the central atom, and that's it, just the atoms. Electron group geometries describe the shape in terms of everything surrounding the central atom. So if you have atoms around it, great. If you have lone pairs around it, we're going to count those too. Now, what I like to think of is that we have a bunch of different electron pair geometries, and I think of them as an umbrella. And under each different electron pair geometry, we have multiple possible molecular geometries. So if you know your electron geometries well enough and you can relate those to specific molecular geometries, it helps with determining shapes. Now you need to be able to determine both the molecular and electron pair or electron group geometries. Talk about how. So again, electron pair geometries are really defined as the arrangement of electron pairs in space. And again, I hate that word pairs. We're going to use groups in space. Groups is much better, and we'll see why later. Molecular geometries are the arrangements of atoms specifically in space. Now, we're going to talk about electron pair / group geometries first. All right, again, I like to use the word group. There are 5 different electron group geometries that we're going to cover in this class. So the 5 different electron group geometries we cover are linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And within each one of these electron group geometries, there are different possible molecular geometries. So we need to talk about each one in turn. Linear is pretty straightforward. We have 3 molecules in a compound and they form a straight line. Trigonal planar, as with anything that has the word planar in it, is flat. So this is a flat molecule with 3 atoms around the central atom for a total of 4 atoms in the molecule. And each bond angle is about 120 degrees. Now, we're going to go into each of these things in the next couple slides. We're going to break down each one of these electron group geometries in terms of what molecular geometries are possible, what are the bond angles within each molecular geometry within that electron group geometry, as well as how to know you have a trigonal planar electron group geometry versus like an octahedral electron group geometry. So we're going to start with these two first, linear and trigonal planar, and we'll build our way across this table this way. So let's start with linear and trigonal planar. When we talk about a linear molecule, we are referring to a triatomic molecule. All of these electron group geometries are dealing with at least 3 or more atoms in your molecule. If you have a diatomic molecule, the answer is always linear for its shape. Because if you have 2 atoms connected to each other, the only shape you can ever form here is a straight line. So we're never talking about diatomics in this lecture. We're always going to be talking about at least triatomic molecules or more. So again, let's continue talking about linear molecules. So linear molecules occur when there are 2 electron groups around a central atom. Now, again, this is going to be our linear electron group geometry. Now, we have to have at least 2 electron groups. Now, what do I mean by electron groups? So let's look at a couple of linear molecules. CO2 is a perfect example of a linear molecule, and it's also the reason why I hate the words electron pair geometry. When we think about stuff around our central atom, here is our central atom. We need to count groups of electrons around them. And the reason why I like to use the word group as opposed to pair is because this double bond is one group. But if we think about how many pairs of electrons are in that double bond, there are actually 2 pairs. This is why I hate the word pairs, because even though there are 2 pairs in this double bonds, triple bonds, what have you, are always considered a single group of electrons. Now, if we look at the central atom on CO2, there are a total of 2 groups of electrons around it. Now, when we count groups of electrons for electron group geometry, we count everything, every bond, every lone pair around the central atom. And so this is how we can identify a molecule as being a linear electron group geometry. Now, with linear molecules, there's only ever one molecular geometry, and that's linear. That's all you got. There's only one. The bond angle, you should know that as well. Bond angle, right, BA, is for a linear molecule always going to be equal to 180 degrees. All right. So this is an example of a linear molecule. Let's talk about another electron group geometry, and that is, I'm going to call them EGs for electron group geometries, and that is trigonal planar. So kind of trigonal planar are when we have 3 electron groups around the central atom. This around the central atom is always going to be there, so I'm going to probably stop writing it after this. But that's the big deal here, is we have to have at least 3 groups of electrons around the central atom in order for our electron group geometry to be trigonal planar. There are actually 2 different molecular geometries possible if you have a trigonal planar electron group geometry. That's great, but you could have one of 2 different molecular geometries. Now, the first one that I'm going to talk about is trigonal. I can spell, I swear. Planar. So our molecular geo is trigonal planar. This occurs when we have 3 groups of bonding electrons around the central atom. So notice, like, trigonal planar electron group geometry just says we have 3 electron groups. It doesn't specify what type of group that electron group is. When we have a molecular geometry of trigonal planar, that means we have both. We have electron group geometry trigonal planar and a molecular geometry of trigonal planar. That means, yes, we have 3 groups of electrons around the central atom, but all 3 of those groups are bonds. So if we look at this guy, for instance, CH2O is a molecule with a Lewis structure of this, and it has both an electron group geometry of trigonal planar and a molecular geometry of trigonal planar, because we can count 1 group, 2 groups, 3 groups around the central atom. So we know the electron group geometry is trigonal planar. If we look a little bit more closely, though, obviously, each one of these groups is a bond. There are no lone pairs on the central atom here. In this scenario, our molecular geometry is also trigonal planar. In fact, in all of our geometries that we talk about today, if you do not have any lone pairs on the central atom, your molecular and your electron group geometries will be the same name. Now, in this geometry, or in this molecule, our bond angles are going to be equal to 120 degrees. So the angle between these 2 bonds, 120. The angle between these 2 bonds, 120. And the angle between, that's an ugly color, hold on. These 2 bonds is also 120. So let's talk about another example here. The other electron group geometry possible, or I'm sorry, molecular geometry possible for this electron group geometry is angular. An angular occurs when we have 2 bonding groups and 1 lone pair on the central atom. Again, if you count, we still have a total of 3 groups around the central atom, so our electron group geometry is still trigonal planar. A great example of this is SO2. So if we look at the Lewis structure for SO2, it looks like this. Now SO2 has 3 groups around it, right? We have 1 bond here, another bond here, and a lone pair there. When we're counting for electron group geometries, we count all of these. When we're looking at molecular geometry, we only have 2 bonding groups and 1 lone pair, which means it's not a trigonal planar molecular geometry, it's an angular molecular geometry. There is no bond up here where the lone pair is, so our bond angle that we actually care about is just between the double bond and the single bond here. And this bond angle for an angular molecule is slightly different from a trigonal planar molecular geometry. This is going to be slightly less than 120 degrees. So our bond angle, x, whatever it is less than 120 degrees. And this is because lone pairs actually, this lone pair here is taking up a lot more space than the bonds, which means it's going to push these 2 bonds closer together. Okay, so those are our molecular geometries and electron group geometries possible for when we have 2 or 3 groups of electrons around the central atom.